Good evening. Welcome to my talk about parsing Icecast streams. Before I get into that, I want to give you some context about why this work was done. This is MX3. MX3 is a website for Swiss music, Swiss musicians. It's the meeting point between artists, radios, fans, record labels, and so on. And one reason radio stations use it is that they come to the platform to discover new talent, local talent, national talent. In fact, all of the third radios, so Couleur 3, SRF3, and so on, they're co-founders of the platform back in 2006, and they're still partners. You can see here that this specific track has been played on the radio. It was on air. Employees of the radio stations those that have an account can come to the platform and manually tag something as being played by them. But of course, this is a tedious process, so most of it is automated. And this automation was done for a very long time by a third-party partner. They ran a system closer to the broadcasting software. So as far as I know, something involving a Windows file share where the broadcasting system wrote files, text files with the current metadata, then cron jobs running every second, firing Perl scripts that parse stuff, write it to a database, then another Perl script like kind of matching the data, like a whole thing. Needless to say that they, at some point, they did not want to maintain it anymore and wanted to get rid of it at the end of last year, which kind of triggered my research into the topic. It was also limiting before because it was kind of out of our control. This system would get the artist and track data from MX3 from the API, then would do the matching there on its system, then push back the on-air events to the MX3 API. But yeah, this can be simplified. So I tried to look for replacements. I think there's a commercial GraphQL API that provides real-time data for these kinds of things. It was not viable for our use case. And then yeah, it got me thinking. Of course, the first approach was, oh yeah, why don't we put it also on the servers, do something like the system that was there before? Yeah, it's not possible. It's too hard to provision, to deploy, to do anything. Then I realized every radio also has an internet stream, right? You can go to a website, click a button, you hear MP3 or whatever. And they're using mostly one of those solutions. So Shoutcast is the commercial solution that was launched sometime in 98, 99, something like this. And Icecast is an open source implementation, and most radio stations are using Icecast, especially you might imagine the smaller ones, because they don't have to pay for commercial licensing and so on. And yeah, Icecast is kind of like the hidden API to getting metadata about currently playing stuff on the radio. I looked at libraries. There's one for Ruby called Shoutout. It was for me. It's not production ready. There's some problems with the encoding of the metadata. It uses threads in a weird way. Overall, it seemed like it was written by someone who's not that familiar with Ruby. And if I had to fix it myself anyway, I thought, yeah, might as well research other solutions, or at worst, write it myself or take it over. I looked at JavaScript libraries. There's a few that helped me a bit also to understand the protocol. But in the end, reusing a JavaScript library was also a no-go because of the deployment thing. So MX3 is a Ruby on Rails application, so everything was set up in a different way, and introducing this complexity was unwarranted. So I did the next best thing, which is rewrite it from scratch. This is the Git history of my prototype, and this prototype went into production, as all prototypes do eventually, even though they shouldn't. But you can see that at some point I decided, oh yeah, this is good enough, maybe we should add tests and handle edge cases and so on. And then, yeah, after 20 commits or something, yeah, I just, so this was a separate repository, right? Then I kind of vended this into the Rails application, and it ran in production mostly and modified for about 6 to 8 months. So it was a pretty good prototype. I'll show you the code. Some of it is, not quite production ready, but proof of concept ready, and yeah, ship early and look for errors, right? So one aspect, before we get into it, one aspect was how to get test data. Of course, you can run the thing against live radio streams, but if you have automated tests, as this library has, you want to get something stable, something that doesn't depend on the internet. You can work on the train, you can put it on CI, and so on. So what does this do? It just sends an HTTP request to a radio stream, and then we get the first however many kilobytes we want, put this in a file, and you can even add it to your repository. 20K is not that big of a file size. Right, and this allows you to get feedback quickly in a test suite. Yes, there are not that many tests, but they're higher level tests, and they gave me enough confidence to refactor and handle edge cases and so on. And the good thing with writing this as a separate library, a separate repository outside from the application was that it was completely decoupled from Rails. So once I put it back into Rails, well, for one, the test suite continued to be really fast, but also it could be its own thing. I have considered open sourcing this, and I could, but I don't want to really maintain it, right? I'm using it for my own purpose. If someone finds it valuable, why not? But the point is to have a solid system for my use case. Yeah, as a side note, because people, I don't see this in many code bases. Just wanted to give an example of how, to not load Rails in tests. So you could have usually people have something like a test Rails helper, but you can have a test helper that it's really for unit tests. So you load your test framework, whichever it is, and maybe have some way of requiring files relative to the project root in an easy way. And then, you require your test helper, the library, the file that you're on the test, and this is it. And it's really fast. And for example, I have this hooked up to, or running the current test, I have it hooked up to a key in my editor, and I get, sub 100 millisecond response, which is cool. Right, let's get into the protocol itself. So Icecast is a client-server kind of protocol. You make one request to the server, and by default you get all your data. But you can send it an HTTP header, this magical IC metadata header set to 1. It's called the IC protocol, I think, for Icecast or something. And then in response you get some headers as well. So for example, the bitrate, some other metadata that actually I'm not using, and then this is the important one. It's the metadata interval. I'll get to it shortly. So these are the headers, and then in the response body you get binary data. The binary data you get is a block of all your data, then a byte which says how much metadata is about to follow. Then you get the metadata, which looks like something like this. So you always have a stream title equals quotes, and then the name of whatever is passing through. And then afterwards you get new new audio data, and so on and so forth. One thing to note is that the metadata is not necessarily there, so this length byte could just contain the value 0, meaning that, you know, it's not every, well, not every frame, it's not every interval that you get metadata. Usually you get some on the change of a song, so every 3 minutes or so. Right, so I looked at how to get this done with Ruby. I'm not one for including, you know, extra gems, libraries, stuff like that. I don't like projects where you have 6 different networking libraries to that have slightly improved interfaces on top of that, but they each do the same thing. So I wanted to keep it simple, looked at what was in the Ruby standard library, and the API is not great, but it works. In this example, though, this assumes you are doing a request, or you get a finite response. And with an audio stream, with an internet radio stream, you get a, you know, always running request, response, unless the network is down or something. Right, so you can do a streaming, you can handle streaming responses with this read body method, and you get chunks. What I did not like about this is that you don't really have access over how much you read from the response. So I decided to go for a detour, or go lower level, and open the socket directly, because the socket, TCP socket interface in Ruby provides the I/O API, which allows you to read and write exact things. And yes, there's a bit more bookkeeping going on for some things, but for these precise things in the protocol where you want to read this number of bytes, then read this byte, and so on, it made things a bit easier. And again, as I said, I used this in production for 8 months. So one thing to do, first you send some headers. So this is the request. This connection class is just a small abstraction over the socket to put new lines and stuff like that. So I'm sure you're familiar with HTTP. You request a certain path, usually root at the host. Then you send this header, the IC metadata headers, set to 1. I guess 2 empty lines to, well, this is 1 empty line, and then because the right line ends with a, you get it. You end your request, kind of. Yeah, maybe I'm getting this wrong. Anyhow, then you wait for a response. You get the HTTP status in response. This is the line which says, oh, you know, HTTP version whatever 200 OK. So this is from the very first commit. So here I did not even bother looking for, am I getting bad HTTP, this kind of stuff, which version. I just assume, you know, if this public radio has an internet stream, they're probably doing it right. So I wanted to get the whole program done. Right. So then you read some headers. They're split by a semicolon, so you can put them in a hash. And read the one you're interested in, which is the IC meta int header. Have to cast this to an integer, and then you're ready to read some stuff. And again, the first try was really hacky. Just a regular expression against whatever you're getting to fetch the stream title and see if you recognize some strings in the output data. This thing with the unpack one, I found it a bit interesting. So there's a way to unpack binary strings in Ruby. There's 2 methods. One is unpack and unpack one. So unpack returns an array, and unpack one returns just the first element of the array. So you give, as a parameter, you give a directive for the format. And the format can be a number of things, floats and integers and so on. For this protocol, we only need two, the 8-bit signed integer and a string. The directive can be followed by a count, and if you put a star, it just repeats until the end of the input. So, for example, here I decode one character from this string, and here I decode everything. It removes trailing no terminators and spaces and stuff like that. So yeah, I gave it a try, and this works. This is not really interesting data, but it works. And here, oops, we have some trailing garbage, and this is because we read too much data. So how to read just enough data? We can actually use the protocol as intended, which is to read this length bit for the metadata. It's just, the length byte for the metadata. It's a number. There's a fixed block size in the protocol. I think it's 16. And so you know that whatever length you read, you multiply by 16 and you get the size of your metadata. As I said, you don't get metadata at each iteration, so sometimes you have to just continue reading all your data. By the way, you see here we're completely discarding all your data. Right, so same thing as before, you read your metadata, and this is one of the fixes I brought, one of the things I had to fix compared to the original library, which was encoding. Most streams I encountered are actually Latin 1 encoded, ISO 8895-1, whatever it is. Some of them are UTF-8 encoded, and there's no, you could try to guess the encoding, but it doesn't really. I have a fixed amount of radio streams, and I can just parse each one for a bit and try different encodings, and then put it in a configuration somewhere saying, okay, this radio stream has UTF-8 encoding, and this one other is Latin 1. So here we can transcode as we wish. Then I move some of the metadata parsing to a different thing, and then because we actually want to continue reading data, I just yield the title we got to whatever is invoking this method, and we continue on. And the point is that on the other side, you should also try to be as quick as possible to write this somewhere else and not block the main process. Yeah, so that was a bit better, and so this is what actually I shipped in production. And I thought about some of the choices I've done. So one was it didn't really support HTTPS because I'm reading stuff. You could call OpenSSL in there, but then in the end you're basically re-implementing net HTTP. It's not worth it. And also there was just in the end I was not comfortable with doing so much HTTP in this library. So I went back to actually reuse net HTTP, and so I had to find a way to deal with the reading of bytes in a controlled manner. I also get some other things for free. I'll show you in a bit. Right, so the beginning is the same. We get the header back, the response header, and then I introduced this abstraction, the chunked.io. It's a modified version of something I saw from a library called Down. It's a Ruby gem, and I massively simplified it because I didn't want the whole power of having this I/O interface, so I just wanted one or two methods, basically this read method. You can see here I am, as an intermediate, I'm transforming the stream body to an enumerator, and then I can get chunks on demand. Right, so diving a bit deeper into the code side, what read does, so this is the length we want to read. So we start with an empty buffer, and this is the thing that can get us the chunks. We read from the source as many times as necessary until we get the right length. And you have to realize that this read partial reads at most this number of bytes. It could read fewer. And I'll show you the implementation right away. So if the buffer is nil, we get a chunk from the HTTP response. We get the hoped amount of data out of it, and then if we did read more than limit number of bytes, we store the rest in the buffer, and this is an instance variable. So this is actually a stateful thing, and whenever read partial gets called again, buffer won't be empty, so we don't retrieve a chunk yet. We try to push the rest of what was in the buffer, and so on and so forth. So the original library, I took it from, did a bit more to, I guess, make it more efficient. I don't care if I have an extra loop or two, so this was enough. And an interesting thing I discovered was this exception stop iteration, which is something that gets called when you want to stop an iteration from the Ruby enumerator. Fun stuff. And of course, I want to translate it into something more tangible for the library, since we are getting network data. End of file error. I mean, I know end of file is, but yeah, Ruby and Unix legacy and all of these things. Right. Okay, so this is the happy path. What about other stuff? There's redirects. I've encountered redirects. I've encountered of course server errors. So maybe the broadcasting system is down or something. I mean, sometimes you get a 500, and maybe also you made a mistake yourself. So what I want to do is handle those cases and some other things like timeouts and interruptions, socket errors, whatever, in a graceful way. And here the idea is that some things should crash the process. For example, if I have a client error, so if I made a mistake in the code, I want to see this in my bug tracker. But for the rest of the errors, I just want to retry. I can log the errors and so on, but I want it to recover. I introduced an abstraction called attempt. And this code is a bit awkward because I had to make it fit into a slide. But this retries method defines which exceptions I want to rescue, how many retries I want to allow, what delay I have between retries, which takes a lambda because I want to implement a usually exponential backoff for retries, and then extra things you want to do after each retry, extra logging or whatever you want to do. Then, so this code is within the connect method of this Icecast parsing client, and it takes care of the retry logic, and then there's one which is completely oblivious to what's happening outside of it, which is the connect without retries. And this thing here, the validation, it may be over engineering, but what I wanted is if the block crashes for 9 times and then it works for, I don't know, 3 hours, if it crashes again, I did not want to crash the surrounding process, so I said, okay, you know what, once it succeeds once, it's good again, and we reset the counter of retries. Yeah, and here's the implementation. So we increment the number of attempts, we run whatever code we want to run, and I've removed some things, but we raise an error with hopefully with a nice error message about the stack trace and yeah, stuff like that. I also omitted here a logger message about, okay, this is retry number 6, we're retrying in 10 minutes, and so on. And finally, we retry, so yeah, we retry this block. Right, so this adds a bit of stability to the thing. We don't have only one stream, there's like 5, 10, I don't know, at this point 15 radios probably. And you want to, and this is in the context of a Rails application. So even though the process doing this reading is a continuous background process, it's supervised and everything, it still has to write to the database. And if you want to write stuff for 15 different radio streams, which could write at random times, more or less, you have to be careful with how you connect to the database, because you could exhaust your connection pool. And so I adopted the classical, concurrence thing of multiple producers, one consumer, where they communicate with the queue. This is from the threads library in Ruby. Then we have a consumer. So it waits for something to get into the queue. So it blocks here. Once we get an element, we store the information into the database, and then we fire a background process to handle this accordingly. On the producer side, we instantiate our client, we do the parsing of the metadata, and this block is called whenever there's a new title. So whenever there's a new title, we put this into the queue, and it gets processed on the other side. There's a few subtleties. One is, so I'm using Sidekick for this. Sidekick guarantees that the job runs once, but it could run more than once, so you have to not process things twice. Sometimes you get just bad metadata from some radios. I don't know, for one day maybe their like currently playing system is down, so they send the audio but not the description of the audio. You get jingles as well, so what I call jingles is the telephone number or Facebook page of the radio, stuff like that, advertising basically. And you also get partial matches, of course. What I mean is partial matches is that we have tracks in the MX3 database, right? So even if an artist is in the database, they have not uploaded all of their tracks, and we want to notify this artist if the ones they did upload are being played on the radio. And so, yeah, how do you do that? I approach it with Postgres. Postgres has a module called fuzzy string match, and this one has a method for or a function calculating the Levenstein distance, which is the distance between two strings, the number of different characters. So let's start with the band. So let's assume that the track by the artist Mama Jefferson called Fame is being played. So this is what we received. We've parsed the metadata, we've normalized the whole thing, making it as easy as possible to match against what we have in the database. What I do is I want to get the closest match. So I limit to one result. We order by distance, with the closest distance first. And so hopefully we get a band ID along with the distance from the thing that we want to match. Then we do something similar with the tracks of the same band. And by the way, this Levenstein function, it has a faster alternative, I think, called Levenstein less than, which is made for small distances. What it does is it has a threshold. So if you say, for example, the threshold is 4, if the distance is lower than 4, it will compute the exact distance. Otherwise, it gives you 4. I did not use it because if the distance is greater than 3 in this case, I actually don't want this to be recorded as a partial match. For me, it's too far away. I mean, this is more. I've observed this, and this can be, the exact number can be fine-tuned. But there's a threshold beyond which you're just getting. You know, if two artists have the same number of characters in their name, of course it will be in like some kind of distance. It makes no sense to try to match. So in the end, what I've of course translated this into ActiveRecord stuff with sanitization and so on. I get the band and its track, and if both the band and the track are found, I return the track along with the combined score, so the sum of the two distances. And then if this is 0, if the distance is 0, then it's an exact match. If it's not an exact match, then you have a partial match, and this can be presented to an admin who can then accept or reject. And yeah, and this can be fine-tuned, but yeah, this is the thing. And basically, this is it. Thank you for listening.